Good morning, everyone. I have 9 o'clock on my screen here in Wisconsin, so I think I'll get started with some of our introductions. I know people are still filing in, and that's great. So, good morning. We want to welcome you to the third annual Discovery Farms Multi-State Webinar. We appreciate you choosing to spend your time with us this morning. Today, we're going to cover the topic of emerging contaminants and water quality and the role that on-farm research plays in informing these topics. Over the course of the morning, we'll be featuring the work of Discovery Farms programs in Wisconsin, Minnesota, Arkansas, and Vermont. My name is Amber Raditz. I'll be the moderator for the day. I am the Agriculture Water Quality Program Manager at the UW-Madison Division of Extension, which is the Wisconsin home of the Discovery Farms program. This multi-state effort is in place to provide farmers, farm advisors, and interested stakeholders with credible water quality research information. A few housekeeping things for you before we get started. First, we encourage questions and discussions from you. That's what makes these webinars the most interesting. So please put content-related questions in the Q&A box, which is found at the bottom of your screen. Please put questions related to logistics, whether you're having issues with technology or questions about the agenda, any other logistics questions into the chat box to the hosts and panelists, and we'll address those separately from the Q&A for speakers. We want you to know that if you do end up accidentally or intentionally hitting the raise hand button, we aren't going to be taking questions that way. We're going to be taking questions through the Q&A box. So make sure you put them in there. Secondly, if you would like to receive CCA credits for your time here today, we'll show the QR code at the end of the session. At that time, you can scan the code from your phone to register for credits, or put your CCA number in the chat and we can register them for you. There are 2 soil and water credits available for today's webinar. Each state will have 30 minutes of presentation time, including answering questions. Each speaker will answer questions at the end of their talk. There might be some time at the end of the session for questions, but we encourage you to ask questions right away during the speaker time, and also use that Q&A feature to vote for questions that resonate with you. You can upvote questions that you also have. I will provide you with a brief background on the Discovery Farms program, and then Mike Daniels will provide a framing on the role that on-farm research plays in emerging issues and the value of including feedback from farmers into our research projects. Discovery Farms was first established in Wisconsin in 2000. It was formed in response to a call from the agriculture and environmental communities for enhanced on-farm research in the area of water quality. Farmers volunteered to host water quality monitoring stations in Wisconsin to better understand the dynamics of runoff timing, the impact of ag management, and the influence of weather. Over the years, programs have been added in Arkansas, Minnesota, and Vermont. Representatives from each state pursued the determination of Discovery Farms, which is a registered trademark, because of the positive response to the work of the program from farmers, farm advisors, agency partners, and water quality stakeholders. Each Discovery Farms program has to include the 3 pillars of Discovery Farms, including farmer leadership, credible water quality research, and communication of results. Mike, you can go ahead and expand on that introduction and give us our charge for the day to make the most of our time together.
Amber, thank you so much, and it's my pleasure to be here this morning. And we did want to expand a little bit on some of the intrinsic value of Discovery Farms that go beyond just collecting of data. I mean, obviously we collect on farm, and we felt like, and I think the value of this program is the data is on private, real working farms. But we collect baseline data on the impact of agriculture on natural resources, especially water. One thing we have found is doing this observational type research, it has provided greater focus for further research. When we see some of the results, it prompts more further questions. And a lot of our research counterparts have jumped in and said, hey, this is good information. We need to find out. And I'll show an example today when I talk about potassium, what I'm talking about on that. We also need to document the performance of conservation practices. I think that the data sets provide real world on-farm examples founded on data. That is very important so that we can educate people on what's happening with real data. Uh, I think one of the great things that it does too is it facilitates farmer to farmer education. Our farmers are very comfortable speaking at field days on their farm about what we're finding on their farm. Suddenly, that data is not just data that's out there, it's their data. And they want to try to explain how we got there and what they might be able to do differently. And then finally, I think it's able to facilitate a multidisciplinary or multi-agency approach in some cases to assist farmers that can bring together a lot more comprehensive focus and information. I also think that Discovery Farms provide an excellent tour site for field days, which promotes discussion, and it really helps focus what's going on farms with the non-agricultural audiences. There's something about those not familiar with farming, getting on a farm and hearing the farm, they suddenly can see some of the things that farmers face with on a daily basis. But I think when you put all this together, the thing that makes the Discovery Farm program go is the farmer leadership and making the producer a part of the solution process. We don't go out and tell them what to do. We go out and partner with them and provide the science and the documentation of what they're doing and the decisions they're making. And this is very valuable because producers know their capability and their farms better than anybody else. And that's got to be a big part of the solution process. And so these are some of the things that we have observed that we didn't necessarily set out to do, but we felt like we ought to introduce some of these things to you about the benefits of Discovery Farms beyond the data. And okay, I think that's good enough for introduction. Let's get started with the speakers. Our first speaker of the day has already introduced herself, but it's Amber Raditz. Amber has worked with the Discovery Farms and Ag Water Quality for over 15 years in Wisconsin. Amber will provide a bit of context on how climate change is impacting our work to understand nutrient movement. Ellen Albright will immediately follow Amber. We'll discuss nitrogen leaching projects, setup and results from 3 Discovery Farm projects in Wisconsin. Ellen started with the Discovery Farms as a researcher in December 2023. In this role, she assists with maintaining on-farm field sites, data analysis, and visualization, and building research partnerships. Ellen received her BA in biology from Macalester College and her PhD in freshwater and marine sciences from the University of Wisconsin-Madison. So go ahead, Amber and Ellen.
Thanks, Mike. Thanks for that great introduction too. It's easy for those of us that work closely with these programs to just assume that the world knows what happens when you're actually this close to it and how involved those farmers and participants are in our work. So thanks for that. That's really helpful. Ellen, you can go ahead and advance the slide. So what Ellen and I are going to talk about this morning are just some pieces of work that are happening in Wisconsin and sort of the importance of that as we consider the ways that our climate seems to be shifting and the ways that that might impact our understandings of nutrient and sediment movement in Wisconsin. So in Wisconsin, I'll give you an example of what our situation has looked like this year. For those of you who aren't in Wisconsin, in February, we had temperatures up to 70 degrees different days. I'm sure that the soil was not frozen until at least mid-December in most places, or even later than that. So we had a really short frozen ground period this year. Almost no snow. And yesterday, my kids had a snow day at school. And so we got about 8 inches of snow yesterday. Today, our yard is green again. And so this kind of rapid movement in between whatever you call fall, winter, spring, and those changes can really have influence on our nutrient movement within the soil. I've been asked a lot of times this winter what it means for water quality to not have snow cover, to not have really frozen ground, and frankly, from a surface water quality standpoint, it's probably a good thing because we had a more opportunity for infiltration throughout the season when we got any precipitation or melting snow or anything like that. When we're thinking about nitrogen, it may or may not be a different story, and so that's what we'll kind of focus on today. When you're thinking about nutrient movement, the main underpinning principle, you're going to get a whole soil science master's degree in one shot here, is that the loss of nutrients is really just source plus transport. And so when we're thinking about the ways that our weather impacts our actual loss of nutrients, it's mostly in that transport category, but also a little bit on the source. Okay, Ellen, one more. So really what it comes down to is that as we see these changes to our Wisconsin seasonality, and I know we have multiple states on here, but this is pretty critical to Wisconsin, Minnesota, kind of our upper Midwest states especially. As we're seeing those changes to our seasonality, it can really dramatically impact the way that nutrient and contaminant movement happens with water. And we're really learning more about these things while the dynamics of the movement changes. So it's actually a good time to be doing more intensive studies of how these nutrients move, because we're not we're understanding things as they're changing, but that'll give us hopefully a good chance to be set up well for the future to give the best recommendations to farmers. Okay. All right, so in Wisconsin specifically, we are seeing increased precipitation, especially in spring and winter. And that's up by about 20% in a lot of places. And summer and fall is kind of variable. Not sure that it's really statistically significant for the time period that it was really recorded, which is from 1950 to 2018. And so the Center for Climatic Research here at the University of Wisconsin-Madison through the Nelson Institute put a lot of these resources together. I have the citation at the end of my part of the talk, but it really shows that in Wisconsin's not the biggest state, but it still is a really lot of variability among the whole state, which gives us as researchers and advisors some good information about how things can vary across the whole state, and one size certainly doesn't fit all. So keeping in mind that spring and winter are the times that we're going to see increased precipitation. You can go ahead one more. This is really usually what our crops look like during that time of the year. And so if you think about the equation of source plus transport, we still might have some source sitting there from fertilization from the previous crop, breakdown of the crop that's there, any nitrogen that's in the soil already. But we don't have anything that's demanding that nitrogen from the soil, and really no living roots on most of our fields. And so there's been a lot of efforts in the state, as well as your states, to increase the number of cover crops and things like that. And especially from a nitrogen perspective, there's just like a couple pieces to think about, which is the source, which is the amount of nitrogen that we're applying for our crop, and then that transport. And so if we can change the way that this looks, during these time of the year where precipitation is increasing, perhaps we can decrease the transport of those nutrients and also hold on to that source. Okay, then the other piece to think of as relating to nitrogen loss is this change in soil temperature and precipitation type. So if the soil is not frozen for a longer period, or even just has a longer time that it's above 50 degrees, we have an increased potential for nitrogen to be converting in the soil and becoming more available for more of the season. And so that's been something that we've kind of relied on in Wisconsin, is to have those really cold temperatures really slow down that biological activity and really kind of give us a break from nitrogen movement and conversion in the soil. And so this is something that as we're working with our research data and recommendations, considering the fact that we may not be able to depend on that during the season anymore, but also on the trade-off of that, the absence of those really cold soil temperatures might mean that we'll have more success getting things to grow and hold on to that nitrogen for more of the year. So that's my little quick bit of an update and framing on that. I know these are really small print, but I can certainly share these resources with you. They're really widely available, but this was just a few of the resources, especially for the maps that I showed in that. And so I'm going to go ahead and turn that over to Ellen to give you some more details on how Discovery Farms is responding to this need.
Great, thank you for getting us started, Amber. I'm really excited to be here with you all today and share a bit about some of our new in-field nitrate monitoring work and share some preliminary data. Before I get into those specific project updates, I want to start with a bit of context, just reviewing what nitrate is, why we're concerned about it, and then how it can move in the environment. So first things first, nitrate is just one chemical form of nitrogen that we find naturally in our soil and water. Nitrate dissolves easily in water, and this means that plants can take it up through their roots and use it as a nitrogen source. Now we find nitrate naturally in low concentrations in the environment, but there are places where we see elevated concentrations, and that means that there's some human-caused source of nitrate pollution. Some of these sources include agricultural and turf fertilizers, human and animal waste, and atmospheric deposition. And nitrate pollution is a concern because it can lead to contaminated drinking water and some associated public health concerns. The most well-known health issue with nitrate ingestion is infant methemoglobinemia, more commonly referred to as blue baby syndrome. In this condition, nitrate affects the ability of red blood cells to bind to oxygen, and not enough oxygen ends up getting to different tissues around the body. So this is a really serious condition. And it's the rationale for our current drinking water standard here in the US, which requires nitrate concentrations be below 10 parts per million. Now there's a strong causal relationship between blue baby syndrome and nitrate ingestion. There's also some strong correlative evidence that consuming too much nitrate can also be associated with neural tube defects, so a risk during pregnancy, as well as colorectal cancer and thyroid disease in adults. Now, with all of these undesirable health outcomes, the primary exposure route is through drinking water. So now I want to talk a little bit more about nitrate in drinking water, and I'll be focusing in specifically on groundwater, because here in Wisconsin, about 3/4 of our drinking water comes from groundwater sources. Furthermore, around a third of Wisconsin households rely on a private well for their drinking water. And using a private well can put folks at additional risk of nitrate exposure because these wells aren't monitored and regulated in the same way as municipal water supplies. The onus is on the well owner to get the water tested. So let's take a look at sort of the geographic scope of this in Wisconsin. So this is a map of groundwater nitrate concentrations. These data come from private wells that have been tested, and then they're aggregated to the township level, and an average is shown here, color-coded by nitrate concentration. So in Wisconsin, if groundwater nitrate is below 2 parts per million, it's considered kind of natural background levels. But if it's above that, so the green, yellow, and orange on the map, there's likely some source of nitrate pollution. So in Wisconsin, this is happening in the western, central, and south-central, southwest portions of the state. These are areas where we have more coarse textured soils that are vulnerable to nitrate movement down in the soil towards groundwater, and also sources of nitrate contamination. It's estimated that statewide, about 10% of our private wells are not meeting that drinking water standard, 10 parts per million. And depending where you are in the state, the situation can be even worse. For example, where I live in southern Wisconsin, 22% of private wells that have been tested aren't meeting that standard. So all this to say is that we have some serious concerns with nitrate in our drinking water here in Wisconsin. Now, if we want to understand this issue and start to address it, one of the first steps is understanding how nitrate moves through the soil so it can get into our groundwater in the first place. So we're going to look at this in the context of an agricultural soil and annual row crop production, because this example is most applicable to our nitrate work here at Wisconsin Discovery Farms. So I'm sure you knew we couldn't go through this talk without looking at a soil nitrogen cycle. But we're going to keep things pretty streamlined by focusing in specifically on nitrate and the inputs and outputs to the system in the crop breeding zone. So nitrate can come into the system directly as fertilizer. Nitrogen can be applied as nitrate. But then there's also a whole host of microbial processes that happen in the soil that can convert other forms of nitrogen, like organic nitrogen, urea, ammonia, into nitrate. So I think of those processes as another input of nitrate. Once nitrate is in the soil, it dissolves easily in water. That means that plants can easily take it up through their roots, so crops can take it up, use it as a source of nitrogen. But it also means that nitrate can move pretty easily with infiltrating rainwater and snowmelt. So it can move out of the rooting zone and deeper in the soil. This process is called nitrate leaching. It's the process that moves nitrate away from the rooting zone where we want it for crop uptake and starts moving it down towards groundwater where we don't want it. I'd be remiss if I didn't mention one more nitrate loss pathway from this system. That's denitrification. This is another microbial process where nitrate is converted to various nitrogen gases, which are released into the atmosphere. Denitrification is important if we're thinking about the overall nitrogen balance of our field, but it's not something that we'll dwell on for this talk. We're really focused on nitrate leaching from the water quality perspective. Now, building a quantitative and mechanistic understanding of nitrate leaching is still an area of active research. But I wanted to highlight a few conservation strategies that we already have in our toolbox to start to address nitrate leaching. So the practices that I'll highlight here include efficient nitrogen management, cover crops, and some precision ag approaches for low yielding areas. And all of these practices just focus on using nitrogen inputs more efficiently, so they have benefits for local water quality, but they may also have benefits for farm profitability. So just to go through these, starting with nitrogen management, the main idea here is trying to use any nitrogen inputs as efficiently as possible. Some steps to take here include accounting for all nitrogen credits, so legumes in the rotation, manure, irrigation water, and then applying any additional nitrogen at recommended rates, taking those N credits into account. And soil nitrate tests, testing manure nitrogen content, are some great tools to kind of better calibrate these calculations. The next strategy I'll highlight is using cover crops. The main idea here is like Amber mentioned in her talk, is extending the amount of the year we have something growing in the soil, able to take up that nitrate. And from a nitrate leaching perspective, cover crops that are able to overwinter in a particular climate are going to do the best job at reducing nitrate leaching. The last practice I'll mention is taking a closer look at low-lying areas of the field that have poor yields as they commonly flood out. So these are places where there's poor return on investment for nitrogen input costs. And because there isn't a crop vigorously growing most years and there isn't an opportunity to harvest, these areas of the field can be hot spots for nitrate leaching. So these can be great places to consider enrolling that area into CRP or considering other forms of perennial cover. This can have an outsized impact on reducing nitrate leaching and can also help the bottom line. So at this point, we've seen that agriculture can already be a leader in starting to address nitrate leaching. But with any conservation practice, it's really important that we're able to evaluate the efficacy of that practice. That helps us make sure that we're recommending practices that work, so farmers aren't wasting time and money. And it also helps us to fine-tune recommendations so we can get things that work for a wider variety of producers. Now, the data that we've looked at so far, that map of Wisconsin groundwater nitrate concentrations, those data came from well monitoring. But unfortunately, wells aren't giving us a direct measure of nitrate leaching, and they're really hard to link to specific agricultural practices. To illustrate this, I've drawn just a little cartoon here. So you can imagine this as a bird's eye view of an agricultural landscape with a patchwork of different fields, different crops, maybe some different management approaches here. Let's imagine that we have a well monitoring location here. We're measuring groundwater nitrate. Now, the groundwater that we're measuring here likely infiltrated over a really large area, kind of drawn, for example, here. And if we were to change one practice on one of these fields, say we adopted a new conservation strategy on one of these fields, unfortunately, it's really unlikely that we would see some response in nitrate concentration at our well monitoring location, especially over a short time scale. There's just a huge area involved and a lot of other factors that we can't account for. So we really have a need for more localized nitrate monitoring within the field itself. So now I want to talk a little bit about some of the field methods that we're using for our nitrate monitoring work to get this in-field data. So we use a method called equilibrium tension lysimeters. And I know that name is a mouthful and this diagram is a little complicated, but we're going to walk through it in 3 parts. So first, a lysimeter is anything that we install in the soil that we use to measure water and material movement in the soil. So in our case, our lysimeters are these large metal boxes that we bury about 4.5 feet deep, so below the rooting zone. They have a porous metal top that allows infiltrating water to pass through and then be collected in the box. The lysimeters are connected to the surface with water sample lines that we can access and then pump the water out of the lysimeter and analyze it for nitrate and other chemical constituents. So that's the lysimeter part of it. And the equilibrium tension part of the name comes from the fact that we maintain a slight suction within the lysimeter. And we do this to mimic the soil matrix potential, which means sort of the tension at which soil particles hold on to water. So our lysimeter is this big void space that we've put into the soil. And by maintaining a little bit of suction, we make that empty space mimic the soil profile around it, so the water flow will be as natural as possible. I'm a really visual person, so I wanted to include a few field pictures just to give you a better sense of what these instruments look like. So on the left here, we have an example of one of those lysimeters before installation. It's sitting on a truck tailgate to give you an idea of scale. And then the photo on the right shows a lysimeter mid-installation. So we dig big soil pits and then dig into the side of those and install the lysimeter such that the soil above it hasn't been disturbed. At all of our field sites, we dig 4 soil pits in which 2 lysimeters are installed, so 8 total. This allows us to capture some spatial variation. So there's a drone photo there showing some pits in progress. And then the photo on the right there gives you an idea of, kind of halfway through the installation process. Got the soil pit, 2 lysimeters installed on the left and right. And then that mess of tubing is the water sample lines and vacuum lines, which connect the lysimeters to a central power station. At that station, we have data loggers to run that suction program, solar panels, and then that's also where we would access the water sample lines to collect samples. We're measuring a whole host of variables at all of our lysimeter sites. From the lysimeters themselves, we're able to look at the volume of water that infiltrated over a given time period. And then we also analyze that water for nitrate and chloride concentrations. At all of our sites, we're fortunate to partner with some county partners who sample these every 2 weeks. All of our sites have a weather station, which is really important context, so we're not making direct comparisons between wet and dry years, for example. We also have soil temperature sensors, so we know when things freeze and thaw out. And then we do some manual soil sampling as well for the variables I've listed, of which nitrate is a particularly important one. And then lastly, we work with participating farmers to get information on how the field is managed over the study period. As I mentioned previously, one of our goals is to be able to evaluate and quantify how effective different conservation strategies are. So to do this for our projects, we're using an experimental design called before-after control impact. And this means that we divide our study field into 2 areas, control and treatment. And then we also divide our study into 2 phases. The first phase is baseline, where we just monitor what nitrate leaching is like across the whole field, with both sides treated the same. After a couple of years, we enter the experimental phase, where some practice is changed on the treatment side of the field, and we continue to measure both sides. So this study design allows us to produce a data set to achieve a few outcomes. First, more on the descriptive and fundamental understanding side of things, we're able to quantify the timing and magnitude of nitrate leaching events. When does it happen? How much nitrate is lost? Why? So trying to get at some of those associated environmental conditions. And then this also allows us to test the efficacy of conservation strategies. We currently have 3 nitrate leaching study sites across Wisconsin. Our first was installed in fall of 2021 in western Wisconsin. And there, the farmers interested in exploring the effects of cover crops on nitrate leaching. And then this past year, we have 2 brand new sites So one installed in eastern Wisconsin this past summer and another in southern Wisconsin just this past fall. So these projects are all really new, but we did want to share some of our preliminary data from our first site, the site in Pepin County, just to give you an idea of the sort of data that we're collecting from these sites. And again, it's 1 year data, so we're not going to be drawing any big inferences or doing an in-depth analysis, just to give you an idea of the data that we have. So from that Pepin County site, we're going to look at 1 year of data from April of 2022 through March of the following year. And during this time, the field was planted to soybeans. And it will look at drainage and nitrate leaching over this time frame. So starting with drainage, this plot is a time series of drainage. So it goes from April through the end of that year. Our field year does go through March, but we didn't have any drainage events after December for this study year. So I just truncated the time series so we could zoom in on when there was drainage and take a closer look. Here, the blue bars show the total cumulative drainage for those 2-week sampling intervals. And then we have the dashed vertical lines indicating when soybeans were planted in May and when they were harvested again in October. Over the course of this first study year, we had around 12 inches of drainage total. Next, we'll look at nitrate leaching. So this is the same time series along the horizontal axis, but now here on the y-axis, we've plotted nitrate leaching, and we've area normalized that so it's in pounds of nitrogen as nitrate per acre. So units we're more comfortable seeing for nitrogen inputs. And here the dots are showing us the average of those paired lysimeters, and the error bars are indicating our level of uncertainty. And that's related to how different the results were between those paired lysimeters. So big error bars mean we had different concentrations in the lysimeters. And small error bars, we can't even see them, means the lysimeters had really similar values. So over the course of this first study year, we had a lot of uncertainty in the spring, and then quite a bit of variation in leaching overall over the course of the year. But on average, when nitrate leaching did occur, the average loss was about 7.5 pounds of nitrogen per acre. This sort of data collection also allows us to estimate total cumulative nitrate loss over the course of the year. So in this case, that loss was nearly 100 pounds of nitrogen per acre. So again, these are preliminary data, but we're excited for the future of these projects and how they'll contribute to our understanding of nitrate leaching in Wisconsin. And some of that excitement comes from how we see our nitrate work fitting into some complementary nitrogen work that's happening across the state. So I just wanted to close out by highlighting two exciting nitrogen research projects that are currently happening, both on the water quality and agronomic side of things. So for water quality, we're really fortunate to be collaborating with Dr. Stephen Hall's lab here at UW-Madison. They've developed a low-cost lysimeter. It's made out of PVC pipe and a special resin. They're installed for a year and then retrieved and looked at how much nitrate stuck to that resin. So you can look at cumulative leaching over a given time frame. These are installed at 2 of our lysimeter sites, and we're really excited to try to compare the two and hopefully use this more low-cost option to have greater spatial coverage in the field, which is something that our setup isn't capable of doing. And then it's really important, of course, to have companion agronomic information to go with these water quality studies. So we're really excited about a new program that's being offered in Wisconsin called the Nitrogen Optimization Pilot Program. This program offers grants directly to producers to perform N-rate trials on their farm and address a research question they have. So this program will really expand Wisconsin's N-rate trials to a wider variety of operations and address questions of interest to producers. We see one of the goals of this program of increasing nitrogen efficiency is very complementary to our work. So we're excited to see the results of these projects. And overall, our long-term vision is that we can take the knowledge that we gain from our nitrate leaching projects and layer it with the knowledge gained from this other work, with the ultimate goal of building a more holistic understanding of nitrate leaching in our state and continuing to develop recommendations that work for a wide variety of producers. So with that, I'll yield the rest of my time to questions. We'll try to get to as many questions as we can, but if we don't get to yours, you're always welcome to reach out to Amber or myself to continue the conversation. So I'll turn things over to Ivy, who I think is doing our
Yes, thank you both for that. There are a few questions. 2 of them are about lysimeters. What is the tension that you were placing on the lysimeters?
I don't know that number off the top of my head, but I could find out that. Sorry.
And then another one we have here, burying the lysimeters must create a great deal of disturbance to the soil profile. How does that play into or impact the results found by the lysimeters? They said they imagine that digging and burying them might disrupt the soil infiltration.
Yeah, that's a great point. We try to minimize that, like I said, by digging into the side of the soil pit. So the soil directly above the lysimeter hasn't been moved or disturbed. However, we are partnering really closely with Kevin Nazarek, who's done a lot more work with these lysimeters than us. So we're learning from him as we go. And it's likely that we won't end up using some of the early parts of our time series, just because of that initial disturbance. So in his work, he's seen that first year might not be so representative. So it's good to have a long baseline window so you can wait for things to resettle.
Right. And then someone asked, what is the soil texture of the Pepin County location?
Soil texture of the Pepin County location is fairly sandy. And Amber, you can chime in if you have a more specific answer.
Yeah, I actually pulled up Web Soil Survey while we were here, and so
thank you.
loamy sands and sandy loams. So yeah, and at that location, we weren't able to dig the lysimeter into the side of the profile just because it's really sandy, and so there wasn't enough stability of the soil to hold it. So in that case, you do have to be careful about how you put it back in the above the lysimeters, and then also, like Ellen said, having some baseline time to try to let that soil equilibrate a little bit.
And is the soil moisture being monitored at these sites?
Yes, I should have mentioned that. We have automated soil moisture sensors installed as well.
Also, we should mention that that question was from Mark Rickers, one of the original Wisconsin Discovery Farmers. So Mark, it's great to see you on today.
We have a couple more. Regarding the depressions being hotspots, I assume these are areas of especially reduced infiltration and increased surface runoff.
Yeah, the study that I cited there about low-lying areas of a field being hotspots of nitrate leaching were in poorly drained soils with pretty heavy clays. So I think it's still an open question how much results of that study may apply to different soils. That particular study was from heavy clay soils in Central Iowa.
I guess let's do one more question before we move on. Will you have lysimeters in fields that also have tile drainage to see how deeper leaching compares against what is intercepted by tiles?
Yeah, that's a great question. Sites they're not tile drained. And I'm unsure if that's something that we'll pursue in the future. Question for Lindsay, our program manager.
That's right.
Emily,
And also, Tim will have to help me out on where tiles are typically placed. The lysimeters are about 4 feet down. So they might be in kind of similar areas to what we see in typically tile drained landscapes. So maybe they would probably be more like complementary to each other rather than a different measurement. Great questions. Thank you all so much for those. That really makes it fun for us to be able to talk with you about this today. So I'm going to find there we go. I think in the interest of time, we'll make sure that we give our next speakers enough time. We'll keep those questions in the chat, in the Q&A that we haven't answered yet. And so perhaps we'll be able to go back, or Ellen and I can type some answers where possible too. So we'll try our best to get all of the questions that are submitted in the Q&A answered. And if you did submit a question in the chat, go ahead and copy and paste that into the Q&A, because it's just a nice system for other people to see your question, to upvote, and to be able to record that we've answered it. So thank you all so much for that interaction. And thanks, Ellen, for a great presentation. So we're going to go ahead and move on. Our next speakers will be from the Discovery Farms program in Vermont, Dr. Heather Darby and Ivy Krasinski. Dr. Darby is a professor and agronomist with the University of Vermont and the project director for Discovery Farms Vermont. Ivy is a research specialist from the UVM Extension Northwest Crops and Soils program and is the lead for coordinating Discovery Acres. The title of their talk is Monitoring Neonics in Water and Soil from Discovery Farms field sites in Vermont. Go ahead and take it from there.
Okay. You can see the slides, I'm assuming.
Yep.
Yes, looks
Okay.
good. Thank you.
All right. Well, thanks everyone. Appreciate our partnership with the broader Discovery Farms network. And I think we all look forward to brainstorming and coming up with, new ideas and opportunities to share information with all of you and the people that we work with here in Vermont. When we met this year, our team anyway was in the middle of trying to pull together some of the data we collected this year on monitoring neonicotinoids in both water and soil, and also looking at the pests that these neonicotinoids are controlling in our state. And part of the reason we have started to monitor this class of insecticides is because there has been increasing concern around this class of pesticides making its way into water, residing for a longer period of times in soil. And then, of course, I'm sure most people have heard about, potential and real impacts on bees and pollinators in all of our states. So I'm going to give a little intro to neonicotinoids and what we're looking at and kind of why, and then we'll dive into some of the very preliminary work that we have done at Discovery Farms, but also with our on-farm partners, and then talk about where we're going into the future. Okay, so again, I think most people on this call are familiar with neonicotinoids. They're a class of insecticide. We commonly talk about them as neonics. There's a number of them. Here are some of the various neonics that are really common in agriculture. Some of the names you may recognize. I think most all of our, Discovery Farm sites are focused on, row crops. And so clethiodin, imidacloprid, and thiamethoxam, very common in some of those systems. And again, these are active ingredients in insecticides. Probably the most common neonicotinoid utilized here in Vermont is clethiodin. So we'll be focusing on that. That's most of the neonicotinoid measurements that we have done. Okay, so again, the neonicotinoids are very specific really to controlling invertebrates or insects. And they're, selectively more toxic to invertebrates, but certainly can have an impact on vertebrates. And, some of that has been shown in the literature. They have become really widely used. They're very, very popular, mostly because they've been relatively affordable, relatively available, and because, especially when they were first released, they were thought to have much lower toxicity to mammals and humans than many of the other traditional insecticides. So some of the insecticides that we used to use have been sort of removed from agricultural use, and for many crops, neonics took their place, and that definitely was thought to be a huge gain. Neonics are water soluble. They're highly water soluble, and when they are soluble in water or become soluble in water, plants can absorb them easily through their roots and be taken up through their circulatory system. And so for those of you in the, pest management world, that means that they are systemic pesticides, right? So they get up into the plant and can help control the insects in that way. Neonics can be applied as a pesticide spray. I mean, they're used in a lot of ornamentals, golf courses, orchards, vegetables as well. And they're also used most widely as a powder or seed coating. And that's where most of the usage is today. And you can see this graph over to the side where it shows the increase in neonicotinoids over time. And you can see it kind of cuts off at 2015. And there are various reasons for that, but it's not because the usage has gone down. It's just tracked differently now. But you can see the significant increase, especially on corn and in soybeans as well, basically from about 2003 up to 2015. So the usage has gone up quite a bit, more than quite a bit. Okay, so for us on this call and in my work as well, mostly what we're focused on are the neonicotinoids that are used as seed treatments. And back in 2000, kind of where that graph was just showing, very little corn seed was treated with neonicotinoids. Actually, I started my job here at UVM in 2003, and neonic treated corn seed was just kind of coming on the scene here. And you can see, by 2011, the majority of the corn seed was being treated with neonics, and by 2014, and still today, nearly all of the corn seed that's grown in the United States is treated with neonicotinoids, primarily clethodim, but also thiaxanthium. There we go. Soybeans, not as much of that seed is treated. There was very little in 2000. In the year 2000, I think the numbers were around, 10% or less. And then you can see that number has grown as well. Today, it is reported that still about 50 to 60% of the soybean seed being planted in the United States is treated. So, there's broad, wide use of this insecticide every single year across the United States in corn, soybeans, and also cotton. Maybe Mike can speak to that as well. And, use in other crops too, but most of the usage of these pesticides is in treated seed. And that goes for Vermont as well. Okay, so why are farmers using this on their seed? Well, there are early season pests that can cause issues, and traditionally they were significant issues here in Vermont. Pests like white grubs, wireworms, and especially seed corn maggot were, and still can be as well in Vermont, were significant issues for farmers here. Part of that has to do with the fact that we live in a cold climate and we have conducive conditions. So we have cool, wet soils in the spring, usually very slow emergence or delayed emergence because of that. Other conducive conditions are, heavy, I don't want to say heavy, but manure systems where we're adding lots of organic matter and we're also using tillage. So, and also in sod systems, which we have quite a bit of here in Vermont. So we have farmers that are rotating out of sod into row crops, and that generally builds up wireworm and white grub populations that cause issues in row crops. And then also, we have seed corn maggot issues, primarily because of, tillage, lots of tillage in the past, not quite as much today, plow till systems that were predominant, 20 plus years ago, manure being added regularly in the spring, and other organic amendments as well. Again, plow down sods and cover crops. So those conditions at least make our area very conducive to these early season pests. And again, before people were using neonic treated seed, they had insecticide boxes on their planters, and they were dumping in Lorsban or any number of insecticides to basically protect their seed at planting. Now, neonics are systemic, like I said, and I got this nifty little graphic from Penn State Extension showing that it is systemic, but really, the concentration of neonics in the plant declines quite rapidly as the plants, begin to grow bigger and reach later stages. And so again, the neonics are really for early season pests. Some of these pests, go on my next slide, like seed corn maggot, they're not really there because you planted corn or soybeans or even cotton. They're not after your crop. They're after, they're trying to find a spot, essentially. They're maggots, right? So the flies are trying to find a stinky, rotting, decomposing mass of organic matter to lay eggs that then become maggots. And we all know what maggots do, right? They're decomposers. And, if you have that situation in your field and you have these yummy seeds out there at the same time, of course, if you happen to plant right when the flies are in peak flight and laying eggs, you could run into a pretty significant issue. And I've seen these in Vermont over the years, obviously not that much in current time because people use neonic treated seed. Okay. So again, that's what seed corn maggots do. The problem here is that if you're not using some kind of control when you plant, if there is a big outbreak or you happen to be planting, during peak flights and you have a conducive situation, there's no rescue treatments at that point. So it could end up in, replanting if things are bad. Okay, so again, there's no rescue treatments here. There's different cultural practices that, may or may not be feasible for most people. Basically, the faster that corn or soybean or whatever you're growing germinates, the less chance there is of, an insect, pest, or fungus or anything else, taking down the seed before it has a chance to grow. Again, maggots are attracted to decaying matter. So thinking about what situations may be more conducive is really important. They really like plow down legumes. So especially in places like Wisconsin, Minnesota, where you're plowing under alfalfa, you can run into some issues here. All right. Wireworm, that's the other pest. I think a lot of people are familiar with that. Again, wireworms generally build up in sod and other like significant grass crops, and they can, burrow their way into your seeds. So, this is a problem for us as well as grubs. We have significant grub issues. This is a hay field in 2023. Annihilated by white grubs. You could just see piles of them. It was disgusting. But here's a situation where the farmer needed to do something. They were going to plant corn, and the corn needed to be treated with high rates of neonics to basically ward off all these grubs. All right, so the concerns again are that these neonics are, they're getting into the environment. There are lots of them used all across the United States. I'm sure people have heard of some of the issues these have caused with pollinators and bees. Some of that has to do with the neonic seed treatment sort of being lost from abrasion off from the seed. And you can see the dust up in the corner, basically going out you know, in the dust, getting on dandelions and other flowering plants that the bees visit, getting into water, getting on the soil surface. Okay, so that's one way some issues have been seen. Again, it's highly soluble in water, so it can move easily through the soil profile when it's not taken up by the plant. And research out there has actually shown very little of it is moved into the plant, and the rest remains in the soil. Some of the neonics are very persistent. You can see the half-life there of clethiodin, quite long depending on conditions. Okay, so these are some of the issues that are coming up. They've been in the literature for a while here, and some states are taking action, and our state is one of them. So, and New York, which is right next door to us, passed a bill, the Birds and Bee Protection Act in 2023, just recently, with a slow sort of phase out of neonicotinoids in that state, and that includes treated seed. And then in Vermont, H706 is a bill here that was just passed in the House that basically follows the New York Birds and Bees Protection Act, which basically gives us 5 years to phase out neonicotinoids being used outside, on seed, and a variety of other means. So this has not passed in Vermont, but the expectation is that it will. And so that is really why much of this work has started. So we've used our Discovery Farm site as a way to collect some data and learn more about what's happening with neonicotinoids, looking at movement and surface and subsurface water, and then also persistence in soil. So Ivy, I'll let you take it from here. Hopefully I didn't use all our time.
Thank you, Heather. So I'm gonna just provide some background information on our Discovery Farm site, this field season, and the sample collection that we've been doing related to soil and water. So we're here in Vermont on the eastern side of the Lake Champlain, with New York to the west and Quebec up north of us. And here you can see the extent of the Lake Champlain Basin. And on the right here, you can see our project area specifically. Next slide. Thank you. So we're up here in the northwest corner of the state in Franklin County. Our research site is in the Jewett Brook watershed of the St. Albans Bay, which you can see here on the right. We are in an area with a lot of farmland, and there is a growing concern about water quality and agricultural runoff. We also are on heavy clay soils that are poorly drained. So our site, it's in an impaired watershed, which has been identified as a high priority for phosphorus reductions. The St. Albans Bay is shallow bay, and there is a substantial amount of accumulated phosphorus in the sediment, which is being released into the water column over time. So we're seeing frequent eutrophic conditions as a result of that. Next slide. So here we have our Discovery Farms research site. This specific field was chosen because of the topography and the distinct micro watersheds within this field, which you can see in this image here. We have 4 micro watersheds, and we're using a paired watershed design with edge of field monitoring. So 2 of the micro watersheds are on non-tile drained land, and those in those we are only monitoring surface runoffs. Those 2 micro watersheds are what we call north surface and south surface, which you can see here. And these purple circles, these indicate our surface edge of field monitoring stations. And then the other 2 micro watersheds have tile drainage that was installed back in the fall of 2020 at the start of this project. And in these 2 watersheds, which we call north tile and south tile, there's surface and subsurface edge of field monitoring stations. You can see here the white with the red, these circles are marking our subsurface or tile stations. And so this gives us 6 total water monitoring stations, and each one of those 6 has its own ID, which you can see here. So next slide. So this is our site design. Like I mentioned, we have 4 micro watersheds or plots. So this site was installed in the fall of 2020, and then we began the calibration period where we were collecting baseline data from the micro watersheds starting in the spring of 2021. And that calibration period went through the end of 2022 and into the first few months of 2023. During the calibration period, all of these watersheds were managed the same, following typical management practices of farms in this area. And those are the practices we're going to call the control management practices, which you can see described here. And then starting in the spring of 2023, we began our treatment implementation. So the treatment management practices were decided on by our advisory board, and they were intended to represent best management practices that farmers in this area would potentially implement. And we chose to focus on practices related to cover crop termination, so tillage versus no-till and planting green, and manure application, so broadcast and incorporated compared to manure injection. So we have a conventional management on tile drained and non-tile drained land, as well as best management practices on tile drained land, as well as non-tile drained land. And over the past 3 years, we have been monitoring water quality as well as crop production and soil health. We've been analyzing water samples for total suspended solids, total nitrogen, dissolved inorganic nitrogen, total phosphorus, and soluble reactive phosphorus. And then starting in 2023, in the late spring, we also began to collect samples to be analyzed for neonicotinoid pesticide concentrations. And we are collecting soil and water samples for that. Next slide. So to start out, I just want to go over this past season, the rain fall we observed this season. This was an extremely wet year for us in Vermont. We had a flooding event in July. There were some places in Vermont that got over 9 inches of rain in less than 48 hours. We didn't receive quite that much up in our area, but we still had above average rain for this season. So in this graph, you can see the daily precipitation amounts. Those are the blue lines. And then the shaded area in the background is the season total accumulated precipitation compared to the 30-year average, which is the red line. By the end of the year, we had a total of 43.5 inches of rain. That is 6 inches above the 30-year average for our area. And I do want to point out that we actually had a pretty dry late spring in May leading up to planting. You can see here in May and June, we were actually behind on rainfall, and we were planting into soil that was very dry and compact. But after the storms in July that I mentioned, the rest of the season was extremely wet. Next slide. So this is a lot of information here, but I wanted to show that we were sampling soil and water at key points in the season. So we were collecting soil samples early in the season before corn planting as a baseline. And I should point out this field does have a historic use of neonicotinoids, but we wanted to capture a baseline. We also were looking at soil sampling just after corn planting, late June around the time of side dress, and then just before harvest and a late season soil sampling. And then for our water sampling events, we also were trying to capture neonic concentrations in water at those key time points early in the season, at planting, throughout the growing season, and then at harvest. And I do want to give Heather some time to talk about our results. I will just say with water monitoring, it is weather dependent, and we have 4 distinct micro watersheds. So the flow does not always occur at each station, at each event. And you can see that here, for example, in May, like I mentioned, it was quite dry. We only had tile flow. We did not have surface runoff. And then later on in June, we only had surface runoff, for example, at one of the 4 surface stations. So with that, Heather, I'll turn it back over. Oh, one more. And so this shows our field management throughout the season with the precipitation events. The red dots along the bottom here, these are our water sample collection dates. And like I mentioned, we didn't start monitoring for neonics until mid-June, which is why you see the first dots here right around the corn planting. And then we followed that through the season. And you can see some of these major rain events. Around corn harvest, we were kind of on a time crunch with the forecast, and you can see right after we harvested and planted our cover crop, we got almost 2.5 inches of rain. So that kind of ended the season on a wet note there.
So let's talk about some of our results. As Ivy said, we did both soil and water sampling. This was a site, this is a very heavy clay site, very poorly drained. In a rotation, the previous crop was alfalfa, but since it's been included in the Discovery Farms network, it's been in corn silage for 3 years. And there, in those years, there's been a historic use of neonicotinoid treated seed, treated with clethodim. So we did go out before we planted to look at residual neonicotinoids in the soil, and we sampled from 0 to 2.5 inches, and then from 2.5 to 6 inches. And so you can see the pre-plant data. We basically, we were able to detect clethodim in the samples, not all of them. So you can see in the surface samples, 87% of the samples we took 16 samples. We did find an average concentration of 3.95 parts per billion, or micrograms per kilogram of clethodim. And then as we went down to 6 inches, we saw slightly higher concentrations, but in less of the samples. So less than 50% of the 16 samples that we collected, we were actually able to detect neonics. And you can see the detection limit is reported at the bottom of the screen as 2 parts per billion. And so then we planted, went through the season, and we did the same sampling at the very end of the season before things got too cold and the ground got too frozen. And you can see that, again, we were detecting clethodim in the surface soil, 0 to 2.5 inches. The level went up. But again, not all, we didn't find detectable levels in all the soil samples. The detectable limits in the 2.5 to 6 inches went up. So basically we saw more samples, still again, not all of them, with detectable levels of clethodim at the very end of the season. So, we saw some increase, we saw residual neonics from prior years, and then we saw increases in the surface, very similar levels, in 2.5 to 6 inches. But the clethodim was present from prior years, and some left over from the current year, even after all the rain. Okay, so we also measured neonics, trying to get a sense of maybe what was happening with them during the season. And we took a sample shortly after planting, and this was one sample, 0 to 6 inches. We took another sample essentially around the time of top dress, when the corn plants were between the 4th and 6th leaf stage. It was about 35 days after planting. And then again, right after we harvested the corn, we went out and sampled again. And you can see, in that 0 to 6 inches, nearly all the samples had detectable levels of clethodim, and the levels, ranged slightly, but from 3.7 up to 5.2 parts per billion in the soil. So it was, increasing in the number of samples where we were able to detect the neonics. So as Ivy also mentioned, we were sampling water coming out of tiles and coming off the surface of the Discovery Farm site throughout the season. And it was very dry, as she mentioned. I'll show another graph in a second. And so there were a number of samples taken, but these were the dates where we saw detectable levels of clethiodin in the tile or the surface water. And you can see we were observing higher levels coming off the surface than out of the tile. And at the date in July, you can see we saw the biggest concentrations. It looked like essentially a first flush after planting. And we saw the highest concentrations throughout the season. You can see the concentrations decline drastically, moving through tile water or off the surface. And by October or by November, we weren't detecting any clethiodin coming off of the fields, either through the tile or the surface water. Okay, so I just want to go back to the precipitation graph. So as Ivy mentioned, in 2023, we had record precipitation. We had about 44 inches at this site. Most of that rainfall occurring in July. So you can see this little red arrow here, which represents July 3rd. Or around that time, and that's where we saw our highest concentrations of clethiodin coming off from the surface and out of the tile. And you can see between the time of planting, which is this yellow arrow, really until about that time, we didn't have a whole lot of rain. And so it makes sense that that kind of first flush of clethiodin from, planting was coming out, basically between that mid-June and early July. And then after that, even though we continued to see significant rainfall, once we got to November and December, we weren't seeing any neonicotinoids moving off from the field through water. So if we're going to look at loading, not concentration, I have found I don't know actually if I've found any papers that are looking at loading, but we're able to do that at our site. And again, this is the value of these sites. We're able to look at things that other people aren't, and loading is one of them. So these are the sample points where samples were sent in for measurement of neonicotinoids or clethiodin, both in the tile and the surface. And you can see again, that 3rd of July, we saw our highest concentration. So these are all the actual average data points from the micro watersheds. And you can see our highest was a loading rate of around 7 milligrams per hectare of clethiodin coming off during that time on the surface. You can see the loading rates from tile were much lower most of the season compared to surface runoff. So we only detected neonicotinoids in surface runoff 47% of the time. So all the other samples that we took did not have detectable levels. And with the tile, we only detected neonicotinoids 43% of the time. So again, we were taking samples. We were not detecting clethiodin every time we were collecting water. And most of what we were seeing was sort of in those early flushes post-planting when we would get significant rain. All right, so if we're going to look at loading data from the entire season, and this was only summarized up to October 23rd because we didn't see anything after that. And you can, see from the graph, 49% of all the samples were below the detection limit. The average load coming out of the tile was much lower than surface runoff at this particular site. And then we did have some issues in some of the samples with low surrogate recovery because of sediment and some other issues. So, again, these loads may actually be higher, but these were the loads coming out of the different micro watersheds that Ivy was showing earlier. So up to 7 milligrams per hectare and a low of 3.2 milligrams per hectare. All right, so Ivy, are we out of time?
I think we want to have time for questions.
Okay, so I will end here. I will say that this is the beginning of our work. We have other sites, which I'm not able to share. We don't have enough time, where we are looking at crop response, the pests themselves in treated and untreated control sites. And we are also looking at degradation and losses of neonicotinoids at sites that do not have a history of neonicotinoid use, to kind of see where we start and end at the end of the season, and how long, at least in our soils and conditions here, it's taking for those pesticides to degrade out of the soil. So stay tuned, just the start. So I think we'll take some questions from here.
Thanks, Heather and Ivy. We may be able to just take one question, and then to the extent possible, if you guys can address some other ones by typing, and then if there are some that we really should answer live, we could perhaps try to fit those in right at the end. I'm gonna choose the question. I think that's a interesting one about, do ag producers see significant increases in corn or soybean crop when using neonic treated seeds? If not, why are they forced to purchase those treated seeds? Can you just give a little background on like the agronomy piece of that?
Yeah. I think it depends where you live and what your situation is. There are a lot of studies that have been published showing that there is no benefit or minimal benefit, only 5% of the time, depending on what study you look at. And again, these pests are, present in certain scenarios and situations. And, that's where these insecticides would be best utilized and where you would certainly see a benefit. But because of the nature of the pest, people have, I think, been sold on there's no rescue treatment. So there's kind of prophylactic use. And I think somebody mentioned that it's very difficult for farmers to access seed that's also not treated. Seed comes that way. It's not an option to have it or not without a lot of planning and investigation. So.
Yeah, so some choices there aren't up to an individual as much. So
Yeah. Yep.
Lots of tendrils to that
Yes.
question. Yes.
And we'll figure out how that works as neonics are going to be phased out in different parts, of our country. So.
Yeah, an evolving, for sure, an evolving situation. So thank you so much, Heather and Ivy.
Thanks.
And whichever pieces you can answer in the Q&A, please do that. If not, leave them there and we'll try to get to them at the end.
Okay.
So we are going to move to our next speaker. Our next speaker is Tim Raditz. Tim works as the Discovery Farms Minnesota coordinator. His talk today is titled Chloride, Water Quality Impairments and Edge of Field Losses from Discovery Farms Monitoring. So Tim, I can see your slides.
Everything look good?
Yes.
All right, let me see if I can hide these so I can see my screen. There we go. Laser pointer. All right, well, thank you for the opportunity to speak to you today. As Amber said, my name is Tim Raditz. I organize the Discovery Farms Minnesota program for that Minnesota Agricultural Water Resource Center. Today I'll be talking about water quality issues relating to chloride and exploring losses that we have observed at our edge of field monitoring sites and discovery farms in Minnesota and Wisconsin. There has been increased scrutiny recently for chloride and how it is impacting our water resources, and I will dive into that topic today. So why is chloride important in water resources? Well, there are human and aquatic impacts. EPA has set a drinking water standard at 250 milligrams per liter or parts per million. That is the level where they consider it harmful to human health. In Minnesota and Wisconsin, levels of acute and chronic toxicity have been developed for animals and aquatic life in our surface waters. Either 230 or 395 milligrams per liter, depending on what state, is the level for chronic impairment, and 860 or 757 milligrams per liter for acute impairment. Chronic is considered longer-term 4-day exposure, and acute is short-term 24-hour exposure. And they've determined that at those levels, it is detrimental to aquatic life. In Minnesota, there are water resources currently being impacted by chloride. Currently, 50 lakes and streams have been designated as impaired for chloride from the Minnesota Pollution Control Agency. Another 75 lakes and streams are at risk of impairment. And correspondingly, 27% of monitoring wells in the metro area have concentrations exceeding the drinking water standard. If we look at Wisconsin, there are 52 water bodies that are considered as impaired for chloride by the Wisconsin Department of Natural Resources. And in this chart, you can see it down here on the right. So definitely not the most waters, but there is a significant portion of waters that are impacted for chloride. The Wisconsin Chlorides Work Group in Wisconsin, which put out a very helpful report or recommendations on a statewide chloride strategy, a report to the Water Initiatives Steering Committee group. And they produced this map showing chloride concentrations in surface waters across the state. There are areas, as you can see highlighted in yellow there, where concentrations of chloride are higher in our surface waters. Also, if you look at groundwater samples in Wisconsin, courtesy of the UW Stevens Point well water viewer, you can see there are areas where average chloride concentrations are approaching or exceed the drinking water standard. So there are current water resources in Wisconsin as well, where chloride is an issue and having current impacts. So the next question is, where is the chloride coming from? There are many sources of chloride in our environment, the first being de-icing salt, which is our biggest source, used for transportation, but fertilizers, water softening, livestock manure or animal manures, and industrial sources are significant as well. For this talk, because we work with farms, we're going to focus on the agricultural sources. So chloride in agriculture. Chloride is one of the 17 essential plant nutrients. It is considered a micronutrient, even though it is taken up at macronutrient levels. It takes anywhere from 3 to 7 pounds per acre of chloride to produce an average agricultural crop. And this will vary depending on type of crop, yield, and so on. Here's a graphic from Dr. Carl Rosen, who gave a great presentation about chloride in agriculture that you can find at our YouTube channel. It shows how chloride moves in agricultural fields. There are 3 pools of chloride: the soil solution, soil organic matter, and primary minerals. Chloride can be immobilized or mineralized by bacteria in the soil to either become part of the soil solution or organic matter. Chloride can also be weathered from the soil parent material to enter the soil solution. Plants uptake chloride as the anion Cl- via mass flow through the roots. chloride moves with water in the soil profile, very similar to the way nitrate moves in agricultural soils. Inputs of chloride in the system come from atmospheric deposition, plant residues that are not harvested, fertilizers and manures, and losses of chloride, include leaching, surface runoff, crop harvest, and volatilization. Chloride in fertilizer comes from potash, or commonly known as OO60. Potash is a cost-effective form of potassium, another essential plant nutrient, but chloride comes along for the ride with this fertilizer, as 47% of potash is chloride. It is a widely available fertilizer used for crop production. There are alternative potassium fertilizer sources that do not contain chloride, but these fertilizers are harder to find and more costly to use, in some cases 2.5 times greater in cost compared to our potash. Chloride in manure, there's ongoing research by Dr. Melissa Wilson at the University of Minnesota looking at chloride levels in animal manures. And chloride in manure is species dependent and can range from 0.09% to 0.56% of the manure. So manure is an important source of chloride as well. Now that we have established water resource impairments and concerns for chloride and agricultural fertilizers and manures as significant sources of chloride, we will now look into what sort of data we have on transport of chloride. Just having a source does not equate to loss of that source. There is an important transport factor that we need to consider as well. For considering this transport factor, we're going to be looking at our extensive Discovery Farms data set in Minnesota and Wisconsin. This is an edge of field surface runoff and tile drainage data set on agricultural fields. This data was collected with automated equipment and similar methods, was collected from 2004 to the present. We have collected 298 site years of data, 191 site years of surface runoff data, and 98 site years of tile drainage data. And this data is fairly evenly split between the two states. If we look at annual chloride losses as yields in pounds per acre on this y-axis, we can see that throughout our whole data set, there is a difference between the surface and tile numbers, with the tile numbers on the left here and the surface runoff numbers on the right. Each dot in these charts is a site year from a particular site. The data in these charts are represented by box plots with the middle line and the number there representing the median or 50th percentile, the top part of the box being the 75th percentile, and the bottom part of the box being the 25th percentile. So over 50% of the data set is included within these boxes. So as you can see, when we look at tile and surface, we get more total movement of chloride from our tiles compared to surface runoff, with median values of 26 pounds per acre compared to almost 2 pounds per acre. If we look at flow weighted mean concentrations and grouped by tile and surface as well, we can also see there's a difference. Flow weighted mean concentrations are a measure of the total amount of nutrients divided by the total amount of runoff or tile flow in any given year. This is a good metric to focus on the level of nutrients in the field without the impact on the amount of water that moves. If we look at flow weighted mean concentrations of chloride, we see a similar trend with tile having a higher median flow weighted mean concentration compared to surface runoff. These data would tell us that we should focus on tile drainage when assessing chloride movement in agricultural systems. In fact, if we look at only Discovery Farm sites that had surface and tile drainage at the same location, measuring losses from the same field, we can see that a substantial portion of the chloride, anywhere from 79 on our lower end to 94 on our higher end, is transported by tile drainage and not surface water runoff. This data would also point to focusing on tile drainage when considering chloride losses from agricultural fields. And if we just look at the tile data, and these are all tile data, monthly flow weighted mean concentrations for all our sites, we can look at what the levels are and if they vary throughout the year. And we can see that the levels of chloride concentration increase from the beginning of the year up until about May or June, and then decrease again. So there is some change in levels throughout the year, and this is likely due to microbial activity increasing and peaking in the early summer time frame and mineralizing more organic chloride. Looking at just tile drainage again, we can also group the chloride data by different factors. The first one being the state. Now, I always like to put Minnesota and Wisconsin in a competition to see who's doing better. Sort of similar to when the Vikings and Packers play. I like to see that sort of competition. And you can see here that there's very similar boxes for the Minnesota and Wisconsin sites. There are some outliers on the Minnesota side, and we'll talk about those in a little bit. But for the most part, the majority of the data is very similar. Now, if we group sites by sites that have manure application and sites that do not have manure application, we see there is some difference in the boxes and the medians of the data set when we're looking at more 20 parts per million for no manure sites compared to 30 parts per million for some of our manured sites. This difference is not as significant as the differences between surface and tile, but there is still some level of difference, with manured fields having higher concentrations of chloride in the tile water. Now, if we look at just the tile data on a site-by-site basis, we can see that some sites have higher concentrations than others. And I particularly want to focus on our no manured sites and look at, we still have a few sites that have elevated levels of chloride concentrations in the tile compared to others. So about 2 out of the 6 of our no manured sites have higher elevations of chloride. So I think there is some regionality or location specific details for movement of chloride with these tile systems. I think they're just higher in some regions or locations than others because of the location and the chemistry of the soils. Now, if we look at the manured sites, we have 9 sites that have a history of manure application that we're looking at, and we can see about 5 out of the 9 have elevated chloride levels. So a little bit higher in terms of the number of sites, but we still have a number of sites that get manure that have similar levels, similar background levels to the rest of the sites that are on the low end. So in the next few slides, we'll look at some of these sites individually to see if there's any relation between chloride applications with potash or manure and tile chloride concentrations. The first couple we're going to start with are our sites NO1W and WI1. These are sites in northwest Minnesota and in the Red River Valley area. So an area that is very unique to Minnesota, and it is probably why the soil chemistry in that area is very unique, and probably why we're seeing some higher levels of chloride loss at these sites. The first being our NO1W-T site. So it's a tile site with no manure. And these charts are just showing our chloride concentration from tile samples through from October of 2012 to July of 2020. What we're also plotting on here are times when we had a potash application, and those are represented by lines here. And so with these potash applications, we're also assuming some chloride comes with those. So what we're really interested in is to see if there's a jump from prior to the chloride application to after the chloride application. And for most of these, it's really hard to find a significant jump. This one, there is some higher samples, but for the most part, right after application, the samples are really in a similar range. For this application in 2016, we might have seen an increase in sample concentrations from a potash application. But then for these two applications, we really don't see that jump too crazy. And actually in this final application, we actually see a decrease. So we have high background levels of chloride in these tiles, and we have really a lack of consistent spike in chloride after fertilizer applications. Now, if we move on to this WI1 site, this is also in the Red River Valley. It's a tile site with no manure, slightly higher background concentrations. We're in that 40 to 80 milligrams per liter. We see some potash applications. We might have a bit of an increase here after this one, maybe a bit of a jump here, but really similar levels from before and after. And this last application, very similar levels of chloride from before and after fertilizer applications. So again, that a lack of a spike or a consistent spike in chloride after fertilizer applications. Here's another one of our sites with lower background chloride concentrations. We're in that more 15 to 30 range is where most of our sample concentrations are for this site. And again, we're looking for spikes in concentration. We just have a lack of spikes. We might have seen a little spike in this with this application, but for the rest of them, very similar concentrations from before to after that fertilizer application. So again, lower background levels, lack of consistent spike in fertilizer or chloride after fertilizer. If we move on to some of our sites with manure and fertilizer applications, this is WR1. This is a site in Minnesota, slightly higher background concentrations of chloride. Our tile data is in the red and our surface runoff data is in the blue. And, again, we had manure applied on all these points, new tile installed on this field, which is actually interesting. It seems like we had a bit of a jump after that new tile was installed, which I think kind of points to maybe some better drainage provided with that new tile installed at this site. But we really see a lack of, response in chloride concentrations to manure or fertilizer applications. Finally, we have another manured site with lower background levels of chloride concentrations. We're in that 20 to 40 range, pretty typical. Surface runoff in the blue dots, tile drainage in the red. And we have potash applications where we don't see much of a spike. We had swine manure where we maybe saw a bit of a spike from that swine manure application, but then we had another swine manure application where we had very limited spike, maybe even a decrease, similar for this last manure application and potash application. So again, lower background levels, lack of consistent spike after application of manure and fertilizer. So when we're looking at strategies to minimize chloride losses from agricultural areas, I think the 4R approach is a very good approach to take for most nutrients, and I think chloride fits in there as well. In the 4Rs, we want to focus on the right source at the right time, the right rate, and put at the right place. So we recommend following, KCL fertilizer guidelines or potash fertilizer guidelines provided by your state extension service. I think that's always a good place to start. We can look at using band placement of potash. And with those band placements, we usually can reduce the rates to get similar crop yield responses. Also, we could try to time applications closer to the period of when plants are going to uptake. And we could look at using non-chloride potassium fertilizer sources. Again, talked about different options. Potassium sulfate is an option there, but cost and availability are issues with that fertilizer source. So lastly, I just wanted to look at a watershed study conducted by the Metropolitan Council in Minnesota, looking at chloride levels in streams throughout the Twin Cities metro area over a 10-year time period. And here are 18 different watersheds that were monitored and evaluated in all the Twin Cities, or evaluated all in the Twin Cities metro area or on the fringe of the Twin Cities metro area. What's interesting about this study is that land use was defined in each of these watersheds as urban, ag, or mixed levels of land use, and there was a good variety of watersheds with more urban land use at the top of the chart here and more agricultural land use at the bottom. And then if we look at, or if they plotted up average annual median chloride concentrations for these watersheds, and we can see that, you know, when we line them up by the ones at the bottom are generally more agricultural and the ones at the top are generally more urban, we can see a pretty good increase in chloride concentrations for the more urbanized watersheds. And in fact, they even did a regression analysis to check for relationships between land use and chloride concentrations. And chloride was found to be highly correlated with urban land use percentage and not well correlated to agricultural land use. So I think ag does play some role in the chloride discussion, but I think our urban land uses are really a big factor in our chloride losses in our water bodies. So as a summary, chloride is a water quality concern for both drinking water and freshwater aquatic life. There are impairments due to chloride in Minnesota and Wisconsin that are currently having effects. Fertilizers and manures are a large source of chloride in our states, but source does not always equate to loss. We also need to consider transport. If we look at transport on agricultural fields, most is transported via tile drainage and not surface runoff. It seems like we have higher concentrations in certain regions and maybe elevated concentrations on fields that have historical manure application. But we also have a lack of consistent tile concentration response from fertilizer or manure applications. We're just not seeing that response and connection from chloride applications from fertilizer and manure and response in tile chloride concentrations. And lastly, watershed studies from the Metropolitan Council in Minnesota indicate chloride concentration in streams is highly correlated to urban land use and not agricultural land use. So I just wanted to wrap up by putting out these good references to check out. You know, I haven't talked about chloride a lot in the past. It was really interesting to learn more about the issue and work up our data to see what we had to say. But if you're interested in chloride and chloride pollution in Minnesota and Wisconsin, I would highly recommend checking out these resources. The first being that Metropolitan Council study that I talked about in the last part of the presentation. I'd also encourage you to check out the Wisconsin Chlorides Work Group. They had a great document providing recommendations on a chloride strategy. And then also Dr. Carl Rosen gave a real good presentation this past year on chloride in agriculture because it's not a well-researched crop nutrient in terms of agronomics and water quality from fields. So he gave a really good overview, which was the basis for a lot of the stuff I talked about for chloride movement on agricultural soils. So with that, I'd be happy to take any questions if we have any.
Thanks, Tim. That was really interesting. It's interesting to see those data put together for a different reason, although I'm not sure if I agree with the Minnesota-Wisconsin competition piece of it.
Competition is always good.
Right. So, one question, maybe just a typing error, but slide must have said K2O. Was it actually potassium oxide applied, or was it potassium chloride applied?
Correct. That would be it was potash applied, so MOP.
Okay, right. And then a question about the urbanization rate and how that's calculated for the regression plot. Is that a question for you or for
That
that?
would be, I would dig further into that Metropolitan Council report. I know they use some land use layers through GIS to define those categories, but I don't know the specifics on what those categories are.
Right. Just for everybody that's participating, go into that Q&A box and make sure you go toggle to the answered screen because there's Heather and Ivy and Ellen have been doing a great job of answering a lot of those questions in that Q&A panel, and there's some really interesting questions and answers in there. So make sure that you take a minute to go read some of those as well. A question here about chloride in manure. What is the source of chlorine content in manure?
The source of chlorine content in manure, I think it's just something animals digest. I mean, it's in grains, it's in different things that animals eat, so they digest it and it ends up in the manure.
So it's not, it's just naturally occurring chloride as in part of the manure. I know early on in our discovery salts, yep, we had a answer in the chat of salts that animals
Sure.
use. Early on in our discovery farms monitoring, the reason we measured for chloride was really to try to indicate when there had been a manure application close to runoff or things like that. And so we never really intended to talk specifically about chloride, but here we are. So
yeah, people would always ask, why are you guys collecting chloride? And I was like, I don't know. No, it was for that purpose, but it's interesting now that a lot more discussion is happening on chloride, and we actually have a very large data set that can be used to hopefully help address some of the questions that are being directed at agriculture.
absolutely. Awesome. Well, if you still have questions for Tim or for Heather and Ivy or for Ellen and I, make sure you put those in the chat. I'm hoping maybe we'll have a few minutes at the end. But for now, we're going to go ahead and travel south for a session from the Discovery Farms Arkansas program. Today, you met Dr. Mike Daniels earlier. Mike is a soil and water conservation specialist for the University of Arkansas System Division of Agriculture's Cooperative Extension Service and the co-leader of Arkansas's Discovery Farms program. His talk today will be on potassium and sulfate loss in runoff from Arkansas dairy Discovery Farms. Go ahead, Mike. You're still on mute, Mike, if you are saying
Okay,
something.
there we go.
Do you want to turn your camera on too?
It doesn't matter, whatever you want.
Well, we'd like to see you.
Let's see. I don't have control of my camera.
Oh, okay.
The host has stopped it. Okay, now they're letting me. Okay.
There you are.
Can you see my slides, more importantly?
That looks great.
Okay, let's go up to the top. I'm going to talk today. This session's been on emerging contaminants, and we've heard some excellent presentations. I would not consider potassium sulfate at this time contaminants, but it is something that we wanted to look at to improve our soil testing program and our recommendations. We really didn't have an idea of how much potassium and sulfate we're losing in runoff, but because we have the infrastructure in place to monitor fields, we decided to add that. This was a suggestion made by Dr. Nathan Slayton, who was the director of our soil test program. And I think it was really good suggestion. And we found some things that kind of, we know we need to improve upon in this area. Even though it's just my name, I wanted to thank the whole Discovery Farm team. James Burke is leading our sulfate part of this, and everybody's involved in this. So some of them are on today, and I'm thankful for that. But I also want to thank another member of our team, because she's here today working behind the scenes, but Rita Watson, who is one of our Zoom experts in Arkansas, and she's helping with the program today, and we really appreciate her doing that. So let's get into this. Well, I just always want to let you know who's helping sponsor our work. We've got a lot of different sponsors, and they're not all necessarily from the agricultural sector of society. We have them from EPA. We have some private things. This program has got a widespread appeal to a lot of different people, and a lot of different groups, and we're thankful for that. Things that we monitor on the U of A Discovery Farm, and let me get something out of the way here, is we started out just like Wisconsin. We measure the hydrological inputs. One thing we have to measure is irrigation. Our agriculture, especially row crops, is dependent on irrigation. We also the precipitation, the runoff volume. We did nitrogen and phosphorus because they are the primary nutrients of water, freshwater water quality concerns, but we have added potassium and sulfate, and obviously the suspended solids in runoff. In some cases, especially with cotton, we're Dr. Bill Robertson, who's retired now, but he was running some sustainability metrics on what we're doing in these systems. We have started looking at soil health. I noticed on one of Heather's slide, increase infiltration is something we're concerned about, and I'll show you why later. And that's Matt Fryer, who's was out measuring infiltration and talking to farmers about infiltration rates. And then obviously you saw a great presentation on climate change. We're looking at those things too. Now, I will tell you, and this is just some of the pictures of us monitoring. If you've got water on your farm, whether it's a pond, stream, drainage ditch, we're going to try to monitor it, as well as the runoff from the edge of the fields. We also monitor the irrigation amount that goes on. This is just our locations, and it doesn't even show a couple of our horticultural farms where we're working with horticultural farmers now. Some of these have been retired or become inactive. Others have not. I'm going to really focus on the Stevens Kirkpatrick farm on the cotton, and then we'll look at some of these other farms for the sulfate. One thing I wanted to mention, when you get over here into the eastern part of our state, where a lot of our farms are, our soils tend to be somewhat poorly drained or poorly drained. And we do not use tiles. So this is a big difference in our state than the other three states you've heard from. We have a lot of restrictive layers, very restrictive to downward water flow in our soils in eastern Arkansas. And we'd have to put our tile drain so shallow that we just don't tile drain. What we do is we surface shape and do a lot of land leveling, which is an improved NRCS conservation practice, to create a uniform slope. So that we can get water both on more efficiently for irrigation, but we also get drainage. You know, the first question you're asking is, we were all taught in basic soils that K gets fixed in the soil, and we assumed it's somewhat immobile because of the cation exchange. It can be fixed by clays. But really, when you go to literature, very little research has been conducted on K loss and runoff. It almost was an afterthought because they were monitoring runoff of nitrogen and phosphorus. Again, potassium loss in runoff is not a water quality concern that I know of. But what we're finding is that we're getting enough potassium loss in runoff. It is a profitability issue, we feel like, for our farmers. I just wanted to go to this site where we did the monitoring for potassium. This is how he managed this for cotton. You will see that he put on, these are the rates of potassium chloride. I'll show you a soil test in a minute, but in one field where you see the C down on Stevens 4, not only was it muriate of potash applied, but then in that fall, some poultry litter was also applied. And so you can kind of see the application rates there, which are very typical for cotton in our state. If you look at it, we have the pH there. The cation exchange is low. I mean, we have low CEC soils in a lot of cases. You look at the potassium, though, these were optimum soil test rates, but yet he still chose to apply potassium because we have had problems with potassium deficiency in cotton in the past. And so part of the problem we find with potassium runoff may be from the fact that we may be applying potassium on where we already have ample soil test potassium. Okay, this is just the potassium loss by runoff event for 2017, 2018. The scales are different, so it may look like these losses were smaller in 2018, but we had this one big point in April of 2019 that skewed this data. But the thing that jumps out about this when you look at it over the years is we're losing potassium from these fields all throughout the year. It's not just based on when we applied that fertilizer back in May or June. And so we see it across all year. So there's something that we don't understand about the potassium source yet and why we're losing this throughout the year. One thing we did notice very quickly, though, is that we are going through some cycles of climate change where the last 5-year reporting period, NOAA has called that the wettest 5-year period since they've been keeping records in Arkansas in terms of precipitation, but it's also some of the driest years in terms of having drought because we're getting these big rainfall events. We've had more 3-inch rainfalls in this 5-year period than at any other time since they've been keeping records. And what we find is that in some cases, these big rainfalls, and here we just arbitrarily said it at the runoff volume was greater than 1 inch. That in these greater than 1 inch things, we can lose a disproportional amount of potassium. And so the transport mechanism is certainly there. And we are concerned that when you look at how much we're losing in those things runoff. But the other thing I will tell you is that when we look at precipitation, the amount that runs off of these soils, on average, we're losing about 45% of our rainfall each year to runoff. And so we've got to do something. We can talk about the source all day long, but I think we're going to have to do something to try to alter the infiltration rate here. These are just the cumulative losses. And again, you can, and I think this shows when these losses are being lost, but you can see there's some probably after potassium fertilizer or muriate of potash application. But then we get out here into the winter months and we see this kind of, and then again, early spring. And we kind of see some of that trend throughout. And so again, it just shows that we're losing this at different times of the year, and some of it may be. But here's what we found. We're losing about 35 pounds of K2O per acre per year. And that's, that's costing us about $26 per acre per year. So, this, and I'll talk a little bit more about that in a minute. But one thing we noticed is that when you compare the losses through irrigation and the losses in rainfall, most of our K losses are coming from rainfall events, not from irrigation events. And I think the reason for that is that we trickle water down these nearly flat furrows, and some of these rows furrows can be a half mile long, and you just don't generate much energy for removing things from the soil. But in our rainfall, we get detachment, but you also get a lot more interaction. And you're filling up that furrow almost instantaneously from top to bottom, and you're creating a lot more energy gradient to perhaps stimulate more mixing of the water and the soil. But we do know it's more of a rainfall issue. Now, it'd be nice if we could find a way to predict our potassium losses just based on rainfall. But like many other rainfall studies, our runoff studies, there's just no relationship. There's so many other factors that affect runoff than just precipitation. There's just really no correlation there whatsoever. a little bit better correlation if you take the actual K loss and the runoff volume, as you might expect, you get a, but like many hydrologists find, these type of relationships are only, and it's really not that good of a fit, but you might start to get a little bit better predictive if you take the natural log of both the runoff volume and the K loss. It's just that there's so much variability in the runoff that you just can't describe the statistics with a bell-shaped curve. There's a lot of skewness, and to remove that, you've got to do mathematical functions like the log. But again, it's still not very predictive, in my opinion. Now, one of the things that our farmers, he's very concerned about this. He saw the amount of potassium he was losing. He said, "What can we do?" We didn't have an answer for it. We're not sure. And this is the example I was talking about, where making these types of observations has led our soil fertility and soil test people to start thinking about ways and practices that would reduce potassium loss and runoff. We didn't realize it was as big a problem as we thought it would be. The farmer wanted to see, if it was actually coming, the potassium was actually coming from the most current fertilizer application, or from the soil. And so what he did is he took one of our smaller fields and decided not to put any potassium down in 2022 and 2023. He did put his normal treatment down on these other two fields, Dumas 2 and Dumas 4. And we see a very similar trend in that the fact that we are losing potassium. This one on the no K applied, even though we're losing at the time we put the fertilizer out, we didn't put any fertilizer out, and we actually lost as much from that field as we did the other fields. But what happened is, and this kind of plays into this idea that in regenerative agriculture we don't have to add fertilizers. The first year he was okay. The second year his yields really dropped down when we had potassium deficiency. So I'm not sure it's something that we can, until we learn how to keep potassium in the field better, that we can just not apply potassium fertilizer. And again, this is an example of farmer leadership. We didn't ask him to do this. This is what he wanted to do to kind of see if he could better understand the situation. So the average loss from 10 site years was about 30 pounds per acre. The average loss was about 46% of what was applied as fertilizer. We're not saying it all came from those fertilizer applications. Obviously, that's not true, but we're trying to make it relative. And loss equates, and now we're thinking it's more like $26 per acre. And we also know the loss is equivalent to about 2 bales of cotton, or a very good cotton yield. And so Dr. Gershon Drescher, one of our new soil fertility, he's gotten some grant money to work on finding ways to hold potassium in that field to make it plant usable, and take advantage of that. And hopefully we may be able to adjust our potassium application rates in the future. Okay, now what about sulfate? We have two sources of sulfate in fertilizers that we typically use in Arkansas: the potassium sulfate, the ammonium sulfate, magnesium sulfate sometimes. They can represent, the adding of these fertilizers can be a substantial portion of our budgets. And we often apply this, and I should have said that by the potassium. The potassium in the previous study was all broadcast, and these fertilizers are broadcast too. And we don't have many that are injecting into the soil or kniving into the soil. We're really broadcasting these for the most part. This grant was funded by the Soil Test Review Board. Like I said, James Burke is leading this. But we wanted to see if we were having the same problems with sulfate being an anion, would it move kind of like nitrates that you saw earlier? What we do know is that it's highly soluble and mobile in soils. And oftentimes people confuse sulfate deficiency with nitrogen deficiency, but the difference is they'll both yellow up. But the sulfate deficiency will only be in the new growth and not in the old growth plant, as as sulfate is immobile in the plant. Here are some of our different locations and the number of fields that we've been using and monitoring this sulfate. You can see the rotations. We tried to do a little bit of work to see, and you might expect differences with different agricultural systems at different locations. We did the edge of field monitoring. We submitted the samples along with our others. We filtered it. We did all the things that you know, when you look at monitoring sulfate that we need to do. We also went back out and did some grid soil sampling just to look to see, but again, with sulfate and its ability to move in soils, this is a snapshot in time. So it's awfully hard sometimes to correlate this to losses that we're seeing. Here are some of our losses though, across the different things. And actually it's kind of interesting that in some of our permanent pastures, in one side anyway, we're a little bit higher than we are in some of our others. The cotton site that we showed the potassium, again, we're high in sulfate runoff from those. If you want to look at it in loading, and these are not flow weighted, but they are just looking at the loading. Again, we see that these numbers are somewhat in the same range as far as loading as our nitrogen and phosphorus, but not quite as high as our potassium. But we are thinking we're losing some, you know, and that it may be something that we need to address in the future. We also looked at, are we losing it during the growing season? Are we losing it in the non-growing season? And this is very typical where we'll find a significant difference in concentration. It would lead us to believe that some of these ammonium or some of these fertilizers that contain sulfate, we might have more loss. We do in concentration, but when you look at factoring in and looking at the weighting or the loading, sorry, not the weighting, but the loading, there's no significant difference. And we see this typically is that a lot of times our concentration will be different statistically, but our loading will not. And I think what we find is that the variability of the runoff is such an order of magnitude higher than the concentration that it just kind of dilutes out the effect from a statistical point of view. And so our observations from this, that significant differences observed in edge of field, land area losses among evaluated discovery farms, that's not too surprising. These are different systems. I mean, permanent pasture versus row crops, different soils. But we did see that we do have some sulfate loss in runoff. You know, I think in many other soils that are not so poorly drained as ours, you might not see as much in runoff. You might see more sulfate leaching, but we just don't have a lot of nitrate leaching and sulfate leaching in our poorly drained or somewhat poorly drained to poorly drained soils because of these very shallow, 6 inches or less restrictive layers to flow. We do think the sulfate losses in runoff may be big, may be large enough that they're decreasing profitability. Because it's highly mobile, we're not sure how to reduce losses. I will say though, I think more and more of this type of data is showing us that while we all focus on the source because that's the easiest to correct, I think that what Heather was saying earlier is we've got to really focus on improving our soil health and our infiltration and water storage and reducing our runoff. And that's something that is going to be, the solutions are not as easy. They're not as responsive. It will take time to alter those soils. But it's something that I think we're going to have to look at. The one thing that we've had success with is cereal rye and breaking up those profiles and letting plant roots get down and water moving down where we're getting water really from 18 inches where we've had cereal rye cover to only 6 inches for that cotton crop where we haven't had a cover. So I'm hoping that maybe cover crops, while there's a lot of different benefits, maybe that's a benefit that's worthwhile for us and will help us with the infiltration problem. For more information, you can obviously go to our social media sites and to our website. And with that, I'll answer any questions. And I hope I did not take more than my share of time.
Mike, you did a beautiful job of managing your time. Thank you so much. And really made us.
But maybe not enough to change my reputation, huh?
Well, you're just so darn pleasant and friendly to listen to. It time just flies usually, right? So we do have one question, and I anticipate maybe some more will come in. Can microbial activity help reduce losses of potassium and sulfate?
I think that is a great question, Amber. I don't think we know enough about the soil microbiology in our row crop areas in our state. We're just starting to do that. Our soil microbiological postdoc that was working on this and still working on it, but he's accepted a job at Wisconsin Platteville. So he's up in Wisconsin now, Dr. Keyshawn Mahmood. But we're hoping to find out and replace him and do more. I think the thing when we look at managing soils, obviously we're attracted and drawn to soil fertility because we can get a quick response. It's very, very important. We do have nutrient deficiencies and we can easily correct that. I think when we look at other aspects of soils like soil microbiology, soil physical properties, we have not spent the time and the research effort looking at those things because we're not quite sure how to get that quick response or how to manipulate that in a way that we can see benefit over a short period of time. But I do think soil microbiology could help us in a lot of ways. And I think that's what this question is implying. But I think we've got to learn more about it to know how to better manipulate it. And we just don't know enough in Arkansas right now. We just have never done that type of work. We're just starting that, really, quite honestly.
Yeah, and I mean, I think the other thing that's really challenging about that type of work is that the results may not be as repeatable as they sometimes are in fertility trials or things like that. And sometimes I listen to like our Rodrigo Worley, our weed scientist in Wisconsin, and talking about these results, and I always think, oh man, that must be so much fun to get those results that are really definitive compared to sometimes water quality or some of these other pieces of the puzzle that are more affected by lots of different things.
Yeah, water quality monitoring and soil health monitoring are very messy. Sometimes we can see some improvement in soil health with the naked eye, but when we go out and transform what we're seeing on the whole field and try to measure it at a point, such as infiltration or something, we don't see the differences that we anticipate.
Mm-hmm.
And so we don't fully understand that yet either. But I do think that perhaps it's worth an investigation looking at soil microbiology and soil physical properties, because there may be some low-hanging fruit there that we couldn't gain otherwise that may affect our soil fertility in the future. And that's why I don't dismiss that or dismiss any regenerative ag type things. I do think we've got to figure out ways to get more out of our soils.
Mm-hmm. Yeah, enhancing that soil function is really, getting that soil to work to help us do the filtering and help us, to enhance that function. And then we can help it out by, feeding it the best that we can, and also being really conscious about our crop management and what we're asking the soil to do for us, basically. So.
Right.
So yeah, I'm gonna go ahead and for those of you that are listening with us, like I said, make sure you go in and kind of check out that Q&A, especially the answered question tab, because there's some really interesting pieces in there. And as we are finishing up here, I want to go ahead and draw your attention to a quick survey that you'll be prompted with as soon as you leave this meeting. So you'll also receive the link to the survey in a follow-up email. So those are the same survey. You don't have to take it twice. So just either when you leave the meeting or when you click on it from the email. But really, those results, I know we're all over surveyed. It is, it's annoying. However, this is not just a survey that goes nowhere. we really use those results. It helps us do a couple things. One of those is to collect that anonymous demographic information so we can evaluate the audiences that we're reaching with this type of work. That's really helpful, especially for those of us that are part of universities that are really working to make sure that we are reaching all of the people that need to be reached with this type of work. So it won't take you too long. Quickly fill that out. It's really helpful to us. We also have a couple of questions in there to kind of assess what you learned from your time at the webinar today, what you're concerned about in this field. And it's just really helpful so that we can keep improving your experience for webinars like this. And so we can help make the most of your time. Your time is really valuable to us. So take a moment to answer that when you leave the webinar. I will go ahead and on behalf of all of us that worked together to deliver this today, we want to thank you so much for spending your time with us, asking those really great questions. And for more info, I also did get a question in the chat about access to presentations or slides or things like that. We are going to record the video of this webinar, or we're going to upload the video of this webinar. It's been recorded. We're going to upload that to the Minnesota Ag Water Resources Center YouTube. And let's see, we do need to put the CCA. There we go. There's the QR code. So you can find this recording at the Minnesota Ag Water Resources Center YouTube page. If you have like a specific slide or presentation that you're really interested in, the best way for you to go about getting more information about that would be to connect directly with the speakers. So we'll make sure that you are connected with the speakers. You can either find us on any of our contact pages, or any of us would be glad to direct you to anyone else. Just because being able to have that additional discussion and context is really helpful for us as presenters and for you as you use that information. So again, thank you for your time. If you have any final questions or logistics things, feel free to add those in the chat or the Q&A, and we can wish you a really good rest of your day.